Okay, next up, I would like to draw the Lewis structures of the following species and give the additional information that is asked for. And so, let's do part A first. So I have SO3. Okay, so as usual, I need to count my valence electrons. I will have S and O3. So S will give me 6 per atom, and oxygen will give me 6 per atom. And so this will all add up to 24 electrons to distribute. Okay, so which one should I place as my essential atom? I have 3 oxygens, 1 S, sulfur, and so it makes the most sense to place sulfur as essential atom. And then let's put a single bond to each oxygen. Let's fill in our octets. Okay, and now let's check. We have 6 by 3 because of each of the lone pairs on each oxygen, plus 2 by 3 because of the bonding pairs, plus 2. That's going to give me 18 plus 6 plus 2. And that is 24 plus 2, which is 26. I have too many electrons. And so I'm going to get rid of this lone pair on the sulfur. And that will leave me with the desired 24. Now let me check on my formal charge. On the sulfur, I will have 6 minus 3 minus 0. So that gives me a large formal charge of plus 3. On each of the oxygens, I will have I will have 6 minus 6 minus 1, giving me minus 1, but then I have 3 oxygens, so that gives me a minus 3 charge in total. So I have minus, 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 plus 3. The net does add up to what it's supposed to be, which is 0, but I have too many charges, and that increases the energy of the molecule to be much higher than it needs to be. And when you ask for the Lewis structure, typically ask for the lowest energy Lewis structure, and so this is not an ideal structure. Its energy is too high. And so how I can deal with this is, first I need to check the periodic table and check, can sulfur take an expanded octet? And so let's just pull one up. Okay, so can sulfur take an expanded octet? And it can. And so instead of having single bonds, I'll have double bonds, and that's how I'm going to minimize those charges. And so I'm going to give each oxygen the double bond it would like. Okay, and so now let's ensure the electrons make sense in terms of octets, ensure I do have the correct number of valence electrons, because I've gone back to the start practically, and so I have 2 by 6 plus 4 by 3. Yeah, and that's going to give me 12 plus 12, which is 24. So my valence electrons are now all accounted for. Now let's double check on that formal charge. On each of the oxygens, I have 6 minus 4 minus 2. 6 valence electrons minus the 4 lone pair electrons minus the 2 it has 1 electron in each bonding pair, so that totals to 2. So 0 on all of them. And on my sulfur, I have 6 minus, it has a single electron in each of the bonding pairs, so that's 6, giving me 0. And so the net adds to what it's supposed to be, and I've minimized it, which was the point. And so this is going to be my best Lewis structure. And now I need to determine whether it's going to be polar or non-polar. So let's go about doing that. So first I count its steric number, and that is the number of groups on my central atom. I have 3 groups, so that's 3. And the notation will be AX3. There's no E, so you can write E0, doesn't really make a difference, just write AX3 would be best. And so now I go ahead, check my Vesper chart. My electron geometry will be trigonal planar. and so my molecular geometry, since I don't have any lone pairs. And so when I draw it, it will look exactly as it did before, because I was informed when I drew it. And that's what it's going to look like. Now I can double check on my dipoles. Oxygen is more electronegative, and so that's going to go that way, that's going to go that way, and that's going to go that way. These two will add to give you an equal vector pointing down, and they will all cancel. And so it's going to be non-polar. Okay, on to our next one. For A, it is non-polar. For our next one, we have PF3. So as we did before, count your valence electrons. So I have PF3. Each phosphorus will give me 5 per atom, and each fluorine will give me 7 per atom. This will add to a total of 21 plus 5, so I have 26 electrons to distribute. Let's put phosphorus in the middle. Fluorine is the most electronegative. It doesn't make sense to have it in the middle. And so let's start with that and fill in everybody's octets. And then see if you have anything left over. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So all of my electrons are taken care of. Now let's go on to check my formal charges. On each of the fluorines, I have 7 valence electrons minus the 6 it has in lone pairs minus the 1 it has in each bonding pair. And that is going to give me a formal charge of 0. On my phosphorus, I have 5 minus the 3 it has in bonding pairs minus the 2 it has in lone pairs, and that is also going to give me 0. And so my net is correct, and it has indeed been minimized. I can't minimize it past 0. So that is going to be my best Lewis structure. And so as usual, I go about finding the steric number now. How many groups do I have on my central atom? And I have 3 bonding pairs plus the 1 lone pair. And so that is going to give me 4. Its notation will be AX3 because I have 3 bonding pairs, E1 for the 1 lone pair. So now when I go to its Vesper chart, I'll look for its electron geometry and its molecular geometry. So as I said, electron geometry doesn't care which ones are lone pairs, which ones are bonding pairs. They're all pairs. It just cares about the way electrons are organized. That's why it's called the electron geometry. And so my electron geometry will be tetrahedral. The electrons are organized in a tetrahedral fashion around my central atom. Now, my molecular geometry cares about the way my atoms are arranged around my central atom, and they're arranged in a trigonal pyramid fashion. So I account for the fact that I have 1 lone pair. Okay, now, just so you know, from this point already, I can tell that it's polar, and the reasoning why is because lone pairs of electrons on my central atom or different atoms mess up the symmetry. A lack of symmetry means that the dipole moments will not cancel, and that means that I will have a non-zero dipole moment. So you don't even need to draw it oftentimes to figure that out if you're trying to be quick, but just for the sake of it, let's draw it. And so I'm gonna have a fluorine here, fluorine here, fluorine here, and then I will have my lone pair going up. Let's fill in everybody with octets. Okay, now we do our dipoles. Fluorine is more electronegative. And then I have a dipole going up because lone pairs are always more electronegative, and they're also destabilizing the angles between the bonds because of the extra repulsion. And so additionally, this dipole will have a different magnitude, and so obviously these 3 won't cancel. The 3 fluorines will add up to a vector pointing down, and then I have a different vector pointing up. So these 2 different magnitude, opposite direction, they will not cancel. And so my net dipole moment is 0. And so that means, sorry, is not 0. And so this molecule will be polar. Let's just go ahead and add that up here. Okay, now for the next one. I have F3SiH. So as usual, let's go about counting our valence electrons. F3SiH. So fluorine gives me 7 valence electrons per atom. Silicon is going to give me 4 valence electrons per atom. Hydrogen is going to give me 1 valence electron per atom. This all adds up to 21 plus 5 again, and that's going to give me 26 electrons to arrange. So I now need to pick my central atom. Fluorine is the most electronegative. It can only make 1 bond, so it doesn't make sense to have that as a central atom. Hydrogen is not as electronegative, but it only has space for 1 bond because it only has the 1s orbital. And so my best choice will be silicon. It's like carbon as it can make 4 bonds. And so let's go ahead and place that. Let's place my 3 fluorines and my 1 hydrogen. So again, as you're doing chemistry, always look at the symmetry. It will tell you things ahead of time. I can already tell that this is not symmetrical. I have 3 fluorines and 1 hydrogen on one side, so those dipole moments won't cancel. I can tell you that right now. But let's go ahead and do it all out so that you can see it. So always try and make a solid prediction on where things should go with your question, and that makes things easier because you learn to look for patterns in the question that will speed up how fast you answer it, and you'll have more confidence in yourself as you learn that your assumptions are oftentimes correct. And so I fill in my octets on the fluorines, and that will leave me with 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. All of my valence electrons are taken care of. Let's go ahead and check my formal charges. On silicon, I'm going to have 4 valence electrons minus the 4 it has, because it has 1 in each bonding pair, and that's going to give me 0. On the fluorine, I'm going to have 7 valence electrons minus the 6 in the lone pairs minus the 1 in each bonding pair, 0. And on my hydrogen, I have 1 valence electron minus the 1 valence electron it's contributing to this bond, and that's going to give me 0 too. And so my net adds up to 0, as it should, and it has been minimized. And so this is going to be my best structure. Now I go on to my Vesper theory. I need to find my steric number. So figure out how many terminal groups I have on my central atom. I have 4 bonding pairs. Its notation will be AX4. And that means that when I pull up the chart, my electron geometry is going to be tetrahedral. And so my molecular geometry, because I don't have any lone pairs, so just go to steric number of 4, 0 lone pairs, tetrahedral, tetrahedral. So, now let's go about drawing that. Okay, and then let's do our dipoles. Fluorine is the most electronegative, and silicon is more electronegative than hydrogen. But the dipole magnitude is going to be different, so let's put it in blue. And so obviously I can see there's no symmetry in the way that these dipoles are pointing, so when I add them, they're not going to cancel, which is what I said initially. And so it will lead you to a net dipole moment that is non-zero. And so again, I have a polar molecule. Okay. Now let's do D and E. So for D, I have SiH3 minus. So as usual, begin with your valence electrons. I have silicon, I have H3, and remember, a minus charge means I have an extra electron that is making it no longer neutral. And so for my silicon, I have 4 electrons per atom. For my hydrogen, I have 1 electron per atom. And my plus charge gives me +1 on the electrons. And so that's going to lead me to 4 plus 4, which is 8 electrons to distribute. Silicon makes the most sense as my central atom. I can't have hydrogen. Place the hydrogens around it. This gives me 2, 4, 6. I have 2 more electrons. Makes the most sense to fill silicon's octet. And so that's what I'll have. Now, check my formal charges. On my hydrogens, it is 1 minus 1, giving me 0. On my silicon, I have 4 minus 3 minus 2, giving me that -1 charge that I was looking for. The net adds to what it's supposed to be, and it is indeed minimized. Hence, this is going to be my best Lewis structure. Now I go about drawing its Vesper. Again, let me just look at it and make a guess on what my answer is going to be. I see a lack of symmetry that is very, very clear. I have 1 lone pair, like it did previously with B. That's gonna destabilize things a little bit and lead you to a non-zero dipole moment. The dipole will not cancel with the other hydrogens. Now let's go ahead and do it, see if that guess was correct. So my steric number, I count the number of electron groups I have around my silicon. I have 3 in bonding pairs plus 1 in a lone pair. So I have a steric number of 4. Its notation will be AX3E1. 3 bonding pairs, 1 lone pair. My electron geometry will only account for how many groups I have, not which ones are atoms or electrons. And so my electron geometry is going to be tetrahedral. My molecular geometry is only looking at the way that the atoms are arranged around my central atom, and that is going to be trigonal pyramid. So let's go ahead and draw that. And I'll have silicon, my 2 lone pairs, and all of my hydrogens. Okay, so already my lone pairs are more electronegative. And then I have silicon, more electronegative, height for all of these. And so these 3 add to a vector pointing up. And we have the vector already pointing up for the lone pair. These obviously will not cancel, and so my net dipole moment is non-zero. And again, I will have a polar molecule. And that's going to be it. So D is going to be polar. Now for our last one, and just a few tips for chemistry and those who will be taking it and are in high school right now and wish to take it in university. Yes, in high school they teach you a lot of these rules that you get used to relying on and you can memorize, but in university you can't do that because you need to think through it and understand what's actually happening, because those rules are given to you at the high school level, so you don't have to think about what is going on down on the level of electrons, so quantum mechanically. That's why you have so many exceptions to these rules, and those exceptions are because of what is going on. And so in university, when you actually do know what's happening, you need to be able to think through it and explain those exceptions oftentimes, like with ionization potentials and atomic radius and all of the above. So for our last one, we have Br2CH2. So contravalence electrons, Br2CH2, I have no charge. Br contributes 7 valence electrons per atom, carbon 4 valence electrons per atom, hydrogen 1 valence electron per atom. That is 14 plus 4 plus 2, and that is going to give me 20 electrons. Okay, now choose my central atom. Carbon can make the most bonds, so I'll have carbon in the middle, and I'll just have 4 bonds attached to it, and arrange my atoms in any way I like. I can put the 2 bromines next to each other. You'll see that it doesn't matter. There's still going to be a lack of symmetry in the dipole moments because of their magnitudes, and so I'll just go with this one for now. Check my formal charges. On each of the hydrogens, I have 1 minus 1, 0. On my bromines, I will have 7 minus 6 minus 1, 0. And on my carbon, I will have 4 minus 4, 0. So the net is as it should be, and the charges have been minimized. So I didn't check if my valence electrons are correct. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So they are. So this is going to be my best Lewis structure. Now I go about its Vesper theory. How many groups do I have attached to my central atom? I have 4 in bonding pairs and 0 in lone pairs, so my notation will be AX4. My electron geometry talks about the way that my electrons are going to be arranged. And so it will be tetrahedral. And my molecular geometry talks about the way the atoms are arranged, and they're also arranged in a tetrahedral fashion because I don't have any lone pairs. So let's go ahead and draw that out. I have C. I'll put the bromine right here. Hydrogen, bromine, hydrogen. Okay, now I'll go about drawing my dipoles. Bromine is more electronegative. Hydrogen is less electronegative. And let's see for that last bromine. And so again, lack of symmetry. This is not pointing down, it's pointing towards you. And so it'll tilt, when it adds to this one, it'll tilt it a little bit and reduce its magnitude upwards just a little bit. So I'll have a net vector roughly pointing up. And for my 2 hydrogens, their angular component will cancel and give me a net vector also pointing up of different magnitude. These 2 obviously cannot cancel each other out, and so I will have a net dipole moment that is non-zero, and so I have a polar molecule again. And so these are all of my answers. Okay, and those are all of the questions I have for you today. I hope you enjoyed today's Q&A session. If you'd like to be notified of when we do post on the channel again, be sure to hit the subscribe button and the bell next to it so you can get the push notification. If you'd like to post questions of your own, be sure to check out the links in the description, as it'll give you access to the OneClass page where we do source our questions. This has been Marlon from OneClass, and I hope to see you next time.